Welcome to the discussion on the chapter Atoms. In lecture 1, we are going to discuss the Thompson's atom model, alpha scattering experiment, its construction and experimental observations. On the basis of alpha scattering experiment, we'll try to understand Rutherford's nuclear atomic model and the limitations of the Rutherford's atomic model. Let us begin with the Thompson's atomic model. Many people from Dalton to Summerfield have given their picture about atom. So in the beginning, the most convincing model of an atom was given by Sir J.J. Thomson. According to Thomson's model, it consists of a positive volume which had electrons embedded here and there. This whole model which we are seeing here, since it appeared as plum and pudding, it is also called plum pudding model. Here we can see that we have a plum and we have a pudding, and inside the pudding here and there we have plums. So if pudding as a whole is the positive matter of an atom, plums acts as electrons embedded. This also can be compared with the watermelon, where the red part of the watermelon is the positive matter, whereas the black seeds can be compared with the electrons. This model suggests that an atom is a tiny sphere of radius 10 to the power minus 10 meter containing the positive charge. The atom is electrically neutral, so it has to contain an equal amount of negative charge in the form of electrons which are embedded randomly inside the sphere. Thomson's atomic model could not explain the observations done by Rutherford's alpha scattering model. So therefore, it was rejected at its base. So after the failure of Thomson's plum pudding model, the failure was basically on the basis of alpha scattering experiment. The alpha scattering experiment is also called Geiger-Masten experiment because Ernst Rutherford made his students Ernst Masten and Hans Geiger to perform an experiment. So it is also called Rutherford's experiment as well as Geiger-Masten experiment. Since it makes use of alpha beam, it is also called alpha scattering experiment. Now, what this experimental setup consists of? It consists of a source of alpha particle which was made to pass through the gold foil. The gold foil scattered the alpha particles in all around the directions, say 360 degree. The scattering of alpha particle is seen using the screen. To go with the experimental setup, the construction of the experiment goes something like this. The whole setup is placed inside the vacuum. Then we have source of alpha particles from where the alpha particles begin. These alpha particles are collimated using the lead bricks, and the alpha particles now are converted into alpha particle beam. The beam of alpha particle further falls on the gold foil of thickness 10 to the power of minus 8 meter, and after that we have a screen where the flash of light is produced when alpha particle strikes it, and the screen is made up of zinc sulfide. Now, to get the appropriate number of alpha particle scattering, we have a movable detector which can move from 0 degree to 180 degree angle. So this is the construction of Geiger-Masten experiment. Now, what was observed on the basis of this experiment? It was seen that most of the alpha particle pass through the foil, which means that they do not suffer any collision with the matter. And only about 0.14% of the incident alpha particles scatter by more than 1 degree. Only 0.14% of alpha particles scattered, making an angle 1 degree. Scattering angle was only 1 degree. And only 1 out of 8,000 deflected by an angle more than 90 degree. When all these observations are taken together in the form of graph, where we plot the graph between the number of scattered particles and the scattering angle, we find that most of the alpha particles goes unscattered, and as the angle increases, the amount of scattering goes on decreasing exponentially. Then what these observations tells? The observation tells that most of the part of the atom is empty. Now, to understand it better, we go with the trajectory of alpha particle in the Coulomb field of target nucleus. The trajectory traced by an alpha particle depends on the impact parameter B of the collision. Here in the diagram, you can see the various vectors are made of the velocities of the alpha particle moving in the direction of target nucleus. Now here we have a factor called impact parameter, denoted with the letter small b. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. If we move away from the nucleus perpendicularly, the impact parameter goes on increasing. And for any alpha particle, if it is exactly in the line with the center of the nucleus, then its impact parameter is 0. The impact parameter is given by the equation B is equal to Z into E square cot of theta by 2 divided by 4 pi epsilon naught m v naught square, where Z is the atomic number, E is the charge of electron, theta is the scattering angle, epsilon naught is the permittivity of free space, m is the mass of the alpha particle, v naught is the initial velocity of the alpha particle, the velocity with which the alpha particle is made to travel towards the nucleus. The second factor that becomes most important in understanding the trajectory of alpha particle is the distance of closest approach R naught. The minimum distance between the alpha particle and the target nucleus when impact parameter B is equal to 0. Now we are speaking about that alpha particle which is exactly in head-on collision with the nucleus. When this alpha particle starts moving towards the nucleus in the line, as it is a positively charged entity, nucleus also being the positively charged entity, when alpha particle approaches nucleus, the nucleus starts repelling it. So the force of repulsion increases as the alpha particle approaches the nucleus. And there exists a minimum distance between the alpha particle and the nucleus from where the alpha particle starts moving backwards by retracing its path. That distance is called distance of closest approach. So that's why it is defined as the minimum distance between the alpha particle and the target nucleus when the impact parameter B is equal to 0. It is given as R0 is equal to 2 ZeQ divided by 4 pi epsilon naught m V naught square. We have to understand that when an alpha particle approaches the distance of closest approach, its kinetic energy is completely converted into electrical potential energy. So here we have what is what? Z is the atomic number, E is the charge. So therefore Z into E together becomes the charge of the nucleus. 2 times of E is the charge of the alpha particle because it contains 2 protons. M is the mass of the alpha particle. V naught is the magnitude of initial velocity and epsilon naught is the permittivity of the free space. So when we understand these things, we find that the alpha particle which is in head-on collision have 0 impact parameter, and as the impact parameter increases, the amount of scattering goes on decreasing. Now on the basis of all these discussions, the Rutherford nuclear model of atom concludes that we have a nucleus at the center and electrons here and there scattered around the nucleus. Now let us try to find out what the conclusions are. So it says that if we compare an atom with the stadium, okay, most of the part in the stadium is empty. And what is the size of the nucleus? If the stadium is an atom, then the size of the nucleus is equal to the size of a grape, which can be kept at the center of the stadium. Try to understand. If we compare an atom and its nucleus with the stadium, then if the stadium is an atom, then the size of the nucleus is that of a grape kept at the center of the stadium. Thus, an atom is almost empty. So therefore, most of the alpha particle passed through the gold foil without scattering, and only few scattered with small angle, say 1 degree, and very few, say 1 out of 8,000 scattered back, making an angle more than 90 degree. But still, the whole mass of an atom is concentrated in the nucleus. Why so? We can understand how dense the nucleus is by comparing this. If I take millions of cars and somehow by crushing or whatever method, if I can put all these cars in a cartoon box of 1 feet by 1 feet by 1 feet, then whatever the density of that box, cartoon box, becomes is the density of the nucleus. So nucleus is very, very dense. Hence, the whole mass of an atom is concentrated in the nucleus. So we say that the entire positive charge and almost whole mass of an atom is concentrated in the small center called a nucleus. The size of the nucleus is of the order 10 raised to minus 15 meter. Of the order 10 raised to minus 15 meter. So hence the size of the nucleus is always measured in Fermi, where 1 Fermi is equal to 10 to the power of minus 15 meter. Thomson already had given the size of the atom. The same thing has been proposed by Rutherford, that the size of the atom is of the order 10 raised to minus 10 meter. The nucleus is surrounded by the clouds of electrons, which makes an atom electrically neutral. Try to understand. The positive charge is at the center in the nucleus, whereas electrons are surrounded around the nucleus in the form of clouds. So this was the experimental conclusions of Rutherford's atomic model. But still, the model failed to explain some of the things which led to the next proposition. New model was proposed. Now let us try to understand what were the limitations of Rutherford's model. The Rutherford's model could not explain the line spectrum emitted by an atom. To understand, when an electron revolving around the nucleus in uniform speed, it should emit the light continuously and lose energy. So, the spectrum produced should be continuous spectrum according to the model. Now, you can understand. So, we have a continuous spectrum where every color have combined with the next one. So, you can't actually distinctly tell where one color have ended and another color have started. If the atom, if it behaved according to the nuclear model, then it would have given the continuous spectrum. But in reality, an atom gives the line spectrum. It is called the discrete spectrum. So the Rutherford model failed in explaining the line spectrum which is emitted by an atom. And if an electron revolves around the nucleus and continuously start giving out energy in the form of light, then the atom should be unstable, because at certain moment the electron will fall inside the nucleus and the atom is lost. The loss of energy due to the revolution around the nucleus should make an electron to move in the spiral path and fall into the nucleus. If this would have happened, then no atom would have been existed. But fortunately, the atom is very much stable. The electron do not fall into the nucleus. So therefore, the Rutherford's model could not explain the stability of the atom. So these two drawbacks were cleared by the next model which was proposed by Niels Bohr. Thank you.